keep it real with emotion. Martians,
Alright, and finally for our tangent graph, okay, so tangent, so this guy, this one looks like this. So let's say we have theta, this is our tangent of theta, okay, here's negative pi over 2, here's positive pi over 2, okay, when you have vertical asymptotes at both of those, if I can actually, there we go, okay, and then they cross at, not cross, sorry, here's negative 1 and here's 1, and then when we're halfway in between, this is at 1, so it looks kind of like this. This is just a rough sketch here, okay, of like an S, and then it just repeats on other intervals there, right? We have other intervals that are going on there. So the thing is, we want to find a domain on which this is 1 to 1, okay? And our domain for this is going to be, we're going to restrict it to negative pi over 2, non-inclusive, because it can't even equal negative pi over 2, right? It's not allowed. Our angle isn't allowed to be negative pi over 2 or pi over 2, because that would make tangent undefined. So we're just going to use the rounded brackets, but this is what's going to be our domain here, okay? That just tells you, like, kind of one cycle there. Alrighty? And so if we just pick that one out, this is what our graph's going to look like, our little segment here. So we're going to have negative pi over 2 here, and pi over 2 there. Again, we have our vertical asymptotes, but we can just kind of ignore everything on the outside of that domain there, our restricted domain, okay? So we have something that looks like this for tangent. Our domain, like I mentioned before, is going to be negative pi over 2 to pi over 2, and our range is from negative infinity up to positive infinity. Okay, so for our inverse tangent, so this is kind of like saying, I don't know, some x is equal to tangent theta, and this doesn't mean like your x coordinate, this is just kind of like a stand-in variable, but our inverse tangent is going to give us something like this. Inverse tangent of some value gives us back our angle, okay? And we're going to flip around those domain and ranges, we're going to switch those up, so our domain is going to be negative infinity to infinity, and our range is going to be from negative pi over 2 up to pi over 2. Okay, and then non-inclusive, meaning it doesn't include the endpoints, okay? So if we graph this, we're going to get something like the following. So if we plug in some value, we get out an angle, okay? And our angle is restricted to, our range is from negative pi over 2 to pi over 2, okay? And it doesn't include those, so that means there has to be horizontal asymptotes there, okay? And our domain, like I said, is from negative infinity to positive infinity. So you can plug in any angle that you want there. Okay, and this graph is going to look like, kind of like a sideways S. Okay, so it'll go like that and it'll kind of taper off toward those horizontal asymptotes there. Alright, so let's see some of these inverse functions in action. So let's evaluate the following two things. So first of all, we're going to find inverse sine of 1/2, and then we'll find inverse tangent of 1. Okay, so let's keep in mind that this whole like inverse thing means the opposite of the following. Sine theta usually equals some value. Let's just call it y. But sine inverse takes your y value and converts it back to an angle. Okay? So what we're really finding in saying inverse sine of 1/2 is equal to some angle means when we kind of convert it back to its inverse, the original function, sine of some angle is equal to 1/2. Okay, so that's kind of the question you should ask yourself, either in your head or on paper, is that when you see something like this, this means, okay, so what angle can I plug into the sine function in order to get out 1/2? Okay, so you can keep this in mind, alrighty, and we're just going to take a look at our unit circle. Okay, so sine is our y value, right? So in order to get a y value of 1/2, our angles have to be pi over 6 or 5 pi over 6. Right? That gives you a positive 1/2. So our options are theta is equal to pi over 6 or 5 pi over 6. But there's one really important thing we have to keep in mind is that in order to use inverse sine, remember we had to get that one-to-one function and we had to restrict our domains, right? And we restricted our domain for sine to be in between negative pi over 2 and positive pi over 2. Okay? So pi over 6 is definitely within that range because negative pi over 2 to pi over 2 is like right in here. So pi over 6 is in there, so that one's good. But 5 pi over 6, that's in the part we ignored. Okay, so 5 pi over 6 doesn't make the cut, and our answer for this one is going to be theta is equal to pi over 6, which is equal to this thing here. So pi over 6 is equal to inverse sine of 1/2. Alrighty, now let's move on to tangent, inverse tangent of 1. Okay, so again, this is like saying, okay, so what angle, we're trying to solve for this angle here, gives us an output of 1, okay? So in this case, we can kind of consider this as to be like sine theta over cosine theta, right? Because that's what tangent is. So this just means, okay, well, when is our sine equal to our cosine? And that would just be simply theta is equal to pi over 4, right? There's also another option of 5 pi over 4, because if we look on our unit circle, here, sine is equal to cosine, and they're both radical 2 over 2. And at 5 pi over 4, they're both equal to negative radical 2 over 2. So when you divide one by the other, that just equals 1 as well. But now we have to consider, okay, what was the domain for tangent? And we said that is going to be not including the endpoints, negative pi over 2 up to pi over 2, okay? And so that's from here to here. So this guy is not included, this whole half of the unit circle, right? So the only one that survives is this pi over 4, okay? So that's going to be the answer for inverse tangent of 1. This is going to be equal to a pi over 4. Even though that looks like a 9, but that is a 4, okay? Okay, so let's try another problem. This says find an exact value for sine of cosine inverse of 4 over 5. Okay, so what? Wait, what? So the thing is, from here, we're going to work from inside to out, okay? So work from inside to out. I think that's usually the easiest way to go, maybe the only way to go, from inside to out when you see an expression like this. So the first thing is to analyze, okay, what's going on with this inverse cosine of 4 over 5? This kind of means that cosine of some angle is equal to 4 over 5, okay? And then our job is to find, okay, so since this guy outputs an angle, then we need to find sine of that angle, right? Because if we can replace this whole thing, this inside, with just an angle denoted by theta, what we're really trying to find is just sine of theta, right? And we can find that by using the Pythagorean identity, which is given by sine squared of theta plus cosine squared theta is equal to 1. Since we already know cosine, we can just figure out sine using this identity. So this will give us sine squared theta plus 4 over 5 squared is equal to 1. Okay, so sine squared theta is equal to 1 minus 16 over 25, which is equal to 9 over 25. So sine, when we square root, we either get the positive or negative of the square root of this guy. So that'd be plus or minus 3 over 5. But we know one thing, because now we're at, okay, do we get the positive answer or the negative answer or both? What's going on here? So the thing is that cosine, negative 1, this inverse cosine function, this only outputs values or angles in between 0 and pi. Remember, because that's the domain that we kind of restricted our cosine function to, which also means that this is the range of our cosine inverse, okay? So since we output only values in between 0 and pi, that means that our sine is only positive, right? Because our y values are only positive from 0 to pi. So we're just going to have to choose that positive value. So we say that, okay, so our answer is going to be a positive 3 over 5. Okay, and that's equivalent to this whole expression here at the top. Alrighty, so that concludes our concepts video on inverse trig functions. I hope that helps, and I'll talk to you in the practice problems video if you watch.